Good morning, all of you. Welcome to the Water Resources Engineering 2, the subject for final year civil engineering. We are in the fourth unit, diversion works. In the previous classes, we discussed about the diversion headworks. So, where exactly a diversion work would be provided? What are the various components like weir, barrage, and what is a weir, what is a barrage, what is the difference between weir and barrage, and what are the similarities between these two as far as the hydraulic properties are concerned, hydraulic functions are concerned, followed by the layout of a diversion headwork, what are the various components, and where they are located, and what is the function of each of the component in a diversion headwork. We discussed, followed by causes and failures of weirs and barrages on permeable foundation. We have discussed basically there are four types of failures of the weirs on permeable foundation, and what are the remedies for this also we discussed. And we concluded the last class with the silt ejectors and silt excluders, where these components will be provided, their location and the purpose and their function, how they work, etc. We discussed about this silt ejector and silt excluder in the previous class. So today we will be taking up the weirs and permeable foundation creep theory, Bligh's, Lane's, Kosla's theories. So all these theories are for determining the uplift pressure and the thickness of the floor to be provided on a permeable foundation. So we have been using this sketch, this figure, even from the previous classes also. This is a weir wall which is resting on a foundation like this. So you may have the foundation extended to the upstream direction as well as in the downstream direction. You can observe here the thickness of this apron or the concrete floor which is provided is varying at a different distances with respect to the weir. You can see here that the thickness is varying. The thickness is varying. And on the upstream side and on the downstream side, it is provided with the sheet piles or cutoffs. The upstream sheet pile and a downstream sheet pile is provided. So these were the provisions which were made and discussed in the last class when we were talking about the remedies. What should be the remedy? You should provide sufficient length and the upstream and downstream, also sufficient thickness of this apron which is required to be provided. This is how we discussed. Similarly, upstream and downstream cutoff piles are to be provided, and upstream and downstream sufficient length or sufficient depth of the sheet piles are to be provided. So this is what we discussed in the previous class. So today we try to look at how to arrive at these thicknesses and what is the basis for it, what are the theories available to arrive at this thickness, and what are the principles involved in calculating the uplift pressure at various points underneath this weir. So this is what we discuss. The aim of this topic, like weirs and permeable foundation, to introduce the theories of percolation, maybe Darcy's law, and then hydraulic gradient theory, to explain about the Bligh's creep theory. So what is this creep? How it is the movement of the flow of water. We discuss what is this creep theories and Bligh's creep theory. What are the limitations of this Bligh's creep theory, and what is the design criteria that is used in Bligh's theory, and then the Lane's weighted creep theory, Kosla's theory, application of the Kosla's theory for the design of a weir and a permeable foundation. Then there are certain correction factors also, like correction for the exit gradient, correction for the floor thickness, correction for the mutual interference of piles, correction for the slope. Okay, so by the method of these independent variables. So these are all the topics which are aimed for this weir on permeable foundation. So the theories of percolation, Darcy's law. The law of flow of water through soil was first enunciated by Darcy in the year 1856 based on the experiments. And this Darcy's law is so simple, stating that the velocity directly proportional to the hydraulic gradient. So V is equal to K into I. V is equal to K into I. I is the hydraulic gradient, which is given to be H by L. H is the head which is causing flow, because you have a weir and there may be a shutter over the crest of the weir. There may not be a shutter also. In both the cases, the head which is provided, which causes the flow, you need to consider from upstream to the downstream portion. And L is the length of the flow path. We come back on saying about this. And K is the permeability coefficient. So the velocity V is equal to K into I, or velocity V is equal to directly proportional to I. Okay. So the Darcy's law, V is equal to K into H by L, the hydraulic gradient. Okay. According to Darcy, the velocity of a flow through pervious medium varies directly as the head causing the flow and inversely as the length of the flow path. So from this equation, you can see that the velocity V is directly proportional to H and inversely proportional to L, inversely proportional to the length of the flow path. Hydraulic gradient theory, and Sir John Oatley and Thomas Hyman stated that in cases where the chief danger to a weir is from the undercover, the true measure of security of a weir on permeable bed is the distance through which the soil, which a current of water would have to travel before it could rise up below the weir. So what is the total length of travel of the water? That is what is called the length of the flow path we have been looking at. So mainly the danger for a weir from the undercover is only the movement of the water through the soil beneath the weir, how much length it is moving, how much length. So the true measure of security of a weir, the stability of a weir, the safety of a weir on permeable bed or a permeable foundation is the distance through which the soil, which a current of water would have to travel before it could rise below the weir. In other words, a reduction of the hydraulic gradient reduces the failure by undercover. So if the hydraulic gradient is less, the chances of failure by the undercover will be less. Undercover will be less. A simple line diagram for a weir is shown here. This line diagram provides you a weir wall which is resting on a foundation, The length of the foundation is given to be ACEB is the total length of the foundation. And for this you have cutoffs, sheet piles which are provided at C, which is called the upstream pile, and another is EF, a downstream pile is provided. Upstream pile, downstream pile is provided. Then H, of course, is up to the water level, up to the crest level, Okay, so this is the simple line diagram, and the assumptions that are made, by the Bligh's creep theory are: number one, percolation water creep along the contact of the base profile of the weir with subsoil, losing the head en route proportional to the length of its travel, and the loss of it varies linearly with the length of creep. So how the percolation water moves? This is what the assumption. Percolation water moves along the contact of the base profile of the weir with subsoil. So you have I'll just go to the previous figure. You have the base profile is like this. So this is all the bottom portion of the weir foundation rather. How this water moves, the length of creep would be along the profile. So how it moves along it will have a contact along the contact of the base profile of the weir. So the contact of the base profile of the weir will be starting from A, it moves to C for a length of L1. From C, how it moves, because there is a sheet pile here, it moves down till the bottom of the pile. Then moves up to the top of this pile. Again moves along the length L2. Here also it moves along the sheet pile, moves down and takes a path, takes a turn and moves along this pile and comes up to B. Follow? So this is what is the length of the creep which is assumed by the Darcy. Bligh, which is assumed by the Bligh. So the assumption is that percolation of water creeps along the contact of the base profile of the weir with the subsoil, losing the head en route proportional to the length of its travel. Whatever is the length, accordingly there will be a loss of head. And the loss of head varies linearly with the length of the creep. The second assumption is the length of the path of a flow has the same effectiveness in reducing the uplift pressure, whether it is along the horizontal or vertical direction. I'll go back once again to the same figure. What is this horizontal flow and vertical flow for this creep length? If you are in the figure, if you are starting from A to C, when the water particle is moving along the soil beneath this, from A to C, it is having a horizontal movement. At the point C, it starts its vertical movement, moves down, then takes U-turn. Once again, vertical movement, moves horizontally, comes to the point E, moves vertically to F, takes U-turn, moves vertically up to the point E, then moves horizontally. So if you have a length of particle of the water, it will have horizontal movement as well as a vertical movement. The length of the path of flow has the same effectiveness in reducing the uplift pressure, whether the movement is along the horizontal direction or along the vertical direction. The effectiveness is same. This is another assumption. Later, of course, this has been contracted, saying that it is a limitation which has been taken up by the Bligh, and you may have a different weightage for the horizontal and vertical movement of the path of the creep. So length of travel is called the creep length and is equal to the sum of the horizontal and vertical lengths of the creep. This is another assumption made by creep. So the total length of creep is equal to the actual movement of the water particle as assumed by creep, consisting of horizontal movement as well as the vertical movement. So the total length of creep equal to the sum of the horizontal and vertical lengths of creep. The fourth assumption made by Bligh: no amount of sheet piling or cutoff could ever stop percolation unless the cutoff extends up to the impermeable strata. So when you are providing a sheet pile or a cutoff, if you have a sheet pile or a cutoff, either on the upstream side or on the downstream side, it will not stop the percolation unless this sheet pile which is provided on the upstream side or this sheet pile which is provided on the downstream side extends to the much deeper unless and until it encounters the impermeable strata. That means if you have more length of this sheet pile which is directly touching the impermeable strata, then only the percolation will be stopped. Otherwise, it continues to flow by taking a U-turn and moves along this sheet pile in the vertical direction. All these assumptions of Bligh were based only on some field observations at some of the weir, like Naroja weir, and because of its simplicity, the theory found general acceptance. So Bligh made certain assumptions which are very serious in nature. Sometimes they may not be very practicable, or they are not very nearer to the practical condition, but still this has been given a lot of acceptance because you got some theory to make the calculations for arrive at the thickness of the foundations at different places. So taking the case of a weir with two piles, and where AB, the profile of the weir, and which is the head causing flow, and CD and EF are the piles provided. So look at this figure, like you have from A to B. So you have AC, CE, CB horizontal lengths. AC, CE, and EB are the horizontal lengths. What about the vertical lengths? CD is the vertical length. DC, once again, this side also is the vertical length. Similarly, EF is the vertical length on one side of the pile. FE is the vertical length of the other side of the pile. If you look at this, if H is the head causing, total head of water up to maximum water level, then the length of the creep would be starting from the point A up to the point B in the figure. Starting from point A up to the point B, consisting of horizontal as well as the vertical creeps. So from A to C, horizontal creep. from C, it is moving down vertically up to point D. The particle is moving down up to point D. So AC plus CD. From D, once again, it is taking a turn like this and moving from D to C, traveling from D to C. So CD plus DC plus C to E, it is coming up to this point. From E, it is moving down. So EF takes a turn and moving vertically again from F to E. So EF plus FE plus EB. So this is all the total length of the creep which has been assumed by Bligh. Accordingly, the total creep length will be, if you have AC is equal to L1 in the figure and CE horizontal length is L2 and EB horizontal length is L3, then you have the depth of the cutoff at upstream is D1, at downstream is D2. You may have same also, but it depends once again on how much the length of the sheet file is provided in order to prevent the wear from the problems, the failures which you have seen, causes of failures and preventive measures. Accordingly, D1 could be equal to D2 or D1 and D2 may be having different lengths also. So accordingly, you have L1 plus D1 plus D1 plus L2 plus D2 plus D2 plus L3, or L1 plus L2 plus L3 horizontal creep plus 2 into D1 plus D2 is the vertical creep length. So the total creep length will be sum of the horizontal creep plus some of the vertical creep. So this is how the total creep length. The loss of head per unit length of creep is the percolation coefficient. So loss of head per unit length. So you know the total length of creep and the total head is known. Total head is H. Total creep length is L. Say total creep length is L. Then H by L is called the percolation coefficient. The reciprocal of this percolation coefficient is called the coefficient of creep C. Coefficient of creep C, and 1 by C is called the percolation coefficient. 1 by C is computed like H by L. Bligh assumed the values of this creep coefficient C for different soils like light sand and mud. The value of C is assumed to be 18 by Bligh. Similarly, fine sand 15, coarse sand 12, and for boulders it is about 9 to 5. The design criteria proposed by Bligh for safety against piping, the length of the creep should be sufficient to provide a safe hydraulic gradient with respect to the type of soil. So safe creep length will be L must be equal to C into H. C is the creep coefficient which he has given from this table depending on the type of the soil, and H is the total head of water there. So C multiplied by H gives you the total safe creep length for safety against piping. For safety against uplift, let H dash be the uplift pressure head at any point on the apron. Then uplift pressure will be equal to gamma into H dash. If T is the thickness of the floor at that particular point and S is the specific gravity of the floor material, then what is the total downward force which is coming? The downward force which is coming per unit area would be equal to the self weight multiplied by unit weight of that material. Self weight will be like per unit area multiplied by thickness T gives you the total volume into the unit weight of that material which is used, maybe a concrete material which is used, will be equal to S into gamma. S is the specific gravity and gamma is the unit weight of water. Gamma is the unit weight of water. So S gamma is the specific weight or unit weight of the material into T thickness multiplied by 1 into 1. In fact, it is per unit area taken. So multiplied by 1 into 1. So T into 1 into 1 is the volume into unit weight gives you the total downward force which is acting. And on one side, you have the uplift pressure force which is acting is gamma H dash, and the downward pressure force would be S gamma into T. So for safety against the uplift, whatever the uplift that is coming must be resisted by the self weight of the material which is used for preparing the apron. So gamma H dash, which is acting vertically upwards, must be balanced by the self weight S gamma into T. So H dash would be equal to gamma gets cancelled. H dash is equal to S into T, or H dash minus T will be equal to ST minus T, subtracting T on both the sides, and s minus 1 into t. S minus 1 into t. In other words, t will be equal to h dash minus t divided by s minus 1. H dash minus t divided by s minus 1. So what is h dash? It is the uplift pressure head. H dash is the uplift pressure head. So if it is deducted with the thickness, you will be getting the net pressure head or head causing flow. So where h is the height of this hydraulic grade line HGL measured above the top of the floor. So the thickness of the apron at any point t will be equal to the height of the hydraulic gradient line at this point divided by s minus 1. S is the specific gravity of the material used for apron. Of course, by providing a factor of safety of 4/3, the thickness of the apron at any required point would be equal to t will be equal to 4/3 into h by s minus 1. So to get the thickness, of the apron at any point, we make use of this equation 4/3 into h by s minus 1. Okay. For the portion of the floor upstream of the barrier, only nominal thickness need be provided. See, when you are providing a weir or a barrage, upstream of that, nominal thickness will be sufficient since the height of water will counterbalance the uplift pressure. See, in the figure, what will happen when you are providing a weir here on the upstream side, though you are extending the apron there, it is not only the weight of the apron which is counterbalancing the uplift pressure, but also the weight of water which is available here. The weight of water which is available here. Since weight of water which is available on the upstream side is more, it doesn't matter even if a nominal thickness of the floor is provided on the upstream side of the weir. So out of the total length of the floor, greater length is provided on the downstream side of the weir. So if you see here from A to this portion is very small, whereas from the downstream portion of the weir to up to the point B, the length is more. The length of the apron is more. After the total length of the floor, greater length of the floor is provided on the downstream side of the weir. However, certain minimum length of impervious floor is always necessary at the upstream of the floor also by providing nominal thickness. Some works designed on this simple theory failed while others stood. This is the issue. By applying this Bligh's creep theory, when the weirs have been designed, some of the weirs are failed. Depending on the extent they ignored or took note on the importance of the vertical cutoff at the upstream and downstream ends. So if upstream and downstream end vertical cutoff is appropriately taken care, then the Bligh's creep theory stood, or the weirs which have been designed based on this theory stood. Otherwise, they failed. So if you just look at here, what is this creep length? I would like to explain from the figure. What is this creep length? So when a upstream cutoff or a sheet pile is provided here, the movement of water particle starts from here, moves in this direction vertically downward up to point B, take a turn at B, flows along this sheet pile again vertically, and reaches this point, junction point, moves horizontally along this. These are like surface contact along with the foundation. So moves along horizontally, and then at this point, just below the weir, you have a small, more thickness of the apron is provided. So it moves in this direction. And if you don't have thickness and provided with the same thickness, it moves directly horizontally. Wherever sheet pile is provided, once again it moves down. Take a turn up to at the point E, moves vertical up to point F. So this is what is the total creep length. This is the creep length. So what is the foundation that we are providing? The thickness of the foundation that we are providing is this portion. This portion just beneath the weir, the foundation thickness is shown here. The floor thickness is shown here. So this thickness may be different at different points. For example, you see a nominal thickness on the upstream side, maybe about 1 meter, on the downstream side, about 1.5 meters is provided here, and so on. However, the thickness may be computed based on the Bligh's creep theory by giving this equation, like the thickness at any point T will be equal to 4/3 into H by S minus 1. It is rho in the figure, is S minus 1. Yes, we are using as a standard notation for the specific gravity. The limitations of this Bligh's creep theory are Bligh made no distinction between the vertical and horizontal creep. This is what we have seen here also. When you are taking the total length of the creep, it is equal to simply the sum of the horizontal creep and the vertical creep. There is no distinction made between the vertical and horizontal creep. Bligh's method holds good as long as the horizontal distance between the upstream and downstream pile lines is greater than twice their depth. In such case, only Bligh's theory is giving good result, or it is giving satisfactory result. What is the condition here? This holds good as long as horizontal distance between the upstream and the downstream piles is greater than the twice their depth. If D is the depth here, or D1 or D2 is the higher depth here, twice the D2 must be there as the distance between these two. The horizontal distance between the upstream cutoff to the downstream cutoff must be equal to or greater than twice the value of this D2. Twice the value of the D2. Then another limitation is Bligh did not consider the idea of exit gradient. We are not talking anything about the hydraulic gradient here. Hydraulic gradient theory has been discussed separately, and Bligh did not consider that. Bligh made no distinction between the outer and inner faces of the piles or intermediate piles. This is another important observation made, which has been a limitation for the Bligh's theory. Just go back once again to the previous figure to show you what is the inner face, what is the outer face of a pile. So you have a sheet pile here. This is one pile. This is one pile. So when you are taking the path of flow of water, so the flow of water is taking place along this arrow, taking a turn, moving up and moving in this direction. So for the pile AB, you have two faces. You have two faces. One face is the outer face, where the movement of the vertical direction flow of water is starting. Then after taking turn, it is moving inside. So this is the outer face of the pile, and this is the inner face of the pile. Similarly, after reaching this portion here, the path of the particle's path would be towards the inner face first, followed by the outer face. So there is inner face and outer face. Bligh made no distinction between the outer and inner faces of the piles. So this may be upstream pile, this may be a downstream pile. In some other cases, you may have some intermediate piles also to provide more safety. We come back once again about that. There may be a pile which is provided in between these upstream and downstream piles is called intermediate pile. Intermediate pile. So Bligh made no distinction between the outer and inner faces of the piles or intermediate piles, whereas according to later investigations, the outer faces of the end piles are much more effective than the inner faces. Also, the intermediate piles of shorter length than the outer ones are ineffective except for local redistribution of pressure. It has been identified later that we need to have the intermediate pile also, and the length of this intermediate pile must be more than the length of the end sheet piles. Otherwise there will be no effect for this intermediate pile except for the local redistribution of pressure. Another assumption, another limitation of the Bligh's theory is that loss of height does not take place in proportion to the creep length, and the uplift pressure distribution is not clear. Uplift pressure distribution, he did not make any explanation about the uplift pressure. Simply, at any point, to find the thickness of the floor, you need to calculate the uplift pressure, and based on this uplift pressure, you have to provide the thickness as 4 by 3 into h by s minus 1. H by s minus 1. And loss of height does not take place in proportion to the creep length. This is another thing. In actual practice, it is different. Bligh did not specify the absolute necessity of providing a pile at the downstream end, whereas it is absolutely essential to have a deep vertical cutoff at the downstream end to prevent this undermining. Bligh, though it has been provided by Bligh at the downstream pile, but it did not give a clear explanation. It did not specify why it is required, what length it is required, why it is required has not been specified by Bligh. This is another limitation. So we have seen about 6 limitations in this Bligh's theory. Later, Ellis modified, and he made a modification on the Bligh's theory. He suggested that seepage water will not travel exactly along the line of contact, but may travel by the shortest route. This is what the Ellis modification which has been proposed by Ellis for the Bligh's theory. So what he has done is that from A, the movement of water will be up to C horizontally. From C, it is moving along the line CD, taking U-turn, moving from D to C again. This is what has been done by Bligh, whereas Ellis stated that it is not like that. It moves in a shorter way. Shorter way is like starting from A, moving up to D. Okay. And from D, it moves up to F. And from F, it moves up to P. This is what the creep length modified by Ellis. So AD, the diagonal distance, plus DF plus FB. DF, the horizontal distance, and then the FB. This is what has been proposed as the creep length by Ellis. So to get AD, what is required now? If L1 is the horizontal distance and D1 is the length of the depth of cutoff of the sheet pile, then square root of L1 square plus D1 square will be equal to AD. So square root of L1 square plus D1 square is AD plus L2 and this distance once again L2 square root of L3 plus D2 square. L3 plus D2 square is provided by Ellis. So Lane recommended a separate theory. This is what is called Lane's weighted creep theory. So Lane recommended a weighted line of creep in which horizontal contacts with the foundation and slopes flatter than 45 degrees being less liable to have the intimate contact and are given a weightage of 1/3. So it tries to give weightage. To arrive at the length of the creep with respect to the horizontal contact and maybe a vertical contact, which is flatter than 45 degrees or being less liable to have the intimate contact is the main proposal by the Lanes. Lane's weighted creep length is the sum of all the steep and vertical contacts plus 1/3 of the sum of the flatter and horizontal lines between the head and the tailwater following along the length of the contact surface of the base and the cutoff. So what he tried to say is that horizontal creep is different from vertical creep, and you cannot make sum of horizontal and vertical as proposed by Bligh is one thing. Second is that you cannot go diagonally also. Square root of L1 square plus D1 square also is not correct. But he stated that there is a different weightage for each type of flow. When you have a horizontal flow, when you have a vertical flow, there is different weightage. Summation of all steep and vertical contacts plus 1/3 of the sum of the flatter and horizontal lines of contact between the head and the tailwater flowing along the contact surface of the base of cutoff will be equal to the Lane's weighted creep length. If the distance between the bottoms of the two cutoffs is less than 1/2 of the weighted creep distance between them, twice the distance between them should be used instead of the actual line of creep between them. This is what has been proposed. If the distance between the bottoms of two cutoffs, two sheet piles, is less than half of the weighted creep distance between these two, then twice the distance between them should be used instead of the actual line of creep between them. Lane recommended the following weighted creep ratios and the ratio of the weighted creep distance to head for a different material. He tries to give a weighted creep ratio, Lane's weighted creep ratio for a very fine sand and silt, 8.5. For fine sand, it is 7. For medium sand, 6. For coarse sand, 5, and so on. So the above creep ratios are applicable where filters and downstream cutoffs are not used. Where drains are properly provided but no flow net analysis is made, 80% of the creep ratios shall be used. Where both the drains and flow net analysis are used, 70% of the weighted creep ratios are to be used. Weighted creep ratio shall not be less than 1.5 under any circumstances. Shall not be less than 1.5. Suppose you are taking 70% of 1.6, it may come less, but still you have to use 1.5 only. 1.5 only. Lane's line of creep method has not been accepted universally. This is a limitation. This is also empirical in nature and lacked theoretical background. So we have seen about the Ellis modification for a Bligh's creep theory, starting with a Bligh's creep theory. Ellis modification given by the Bligh's, given by Ellie on the Bligh's creep theory. Lane has proposed for the weighted creep theory. We try to work out one problem on the Bligh's creep theory. The line diagram of a hydraulic structure on permeable foundations is shown below. I'll be reading again. The line diagram of a hydraulic structure on permeable foundation is shown below. So the hydraulic structure here is a weir. In the figure, this is the weir which has been provided on a permeable foundation having upstream length of the foundation as well as the downstream length of the foundation. What more is there? Calculate the hydraulic gradient according to the Bligh's creep theory. Also find the uplift pressures at the points A, B, and C shown in the figure and the thickness of the flow required at these points. This is why this is how the Bligh's creep theory is used. The Bligh's theory is used to find out what is the thickness required at different points along the length of this floor. Along the length of this floor. So at point A, at point B, at point C, what should be the thickness of the floor required? You need to find the uplift pressure at the point ABC and also find the thickness of the floor required. So in the figure, you may note that the total head causing flow here is 4 meters. This is the water which is available. Water which is available 4 meters. That means height of this weir wall is 4 meters, which is resting on this foundation. The length of the foundation is something like starting from this point where you have a upstream sheet pipe. Also, you have a downstream sheet pipe. D1, D2 are given, or you have 4 meters length of the sheet pile here and 6 meters length of the sheet pile here. In between, you have an intermediate pile also. You have one intermediate pile. So upstream, downstream, and intermediate piles are there. A, B, C are the points at which you need to find the uplift pressure as well as the thickness of the floor required. Other dimensions are given. 4 meters is the total height of water here, and 4 meters is the length of the upstream sheet pipe. 4 meters is the length of the intermediate pipe. 6 meters is the length of the downstream sheet pipe. And the location of point A is 5 meters. Location of B is 10 meters. Location of C is 16 meters. And the total floor length is 20 meters given. 20 meters given. So, according to Bligh's creep theory, now you have to find the total creep length. For this, how do we get the total creep length? It is the sum of the horizontal and vertical. Sum of the horizontal and vertical lengths of creep. Sum of the horizontal and vertical lengths of creep will be equal to the total creep length. So, starting from this point A, the water particle is assumed to move vertically downwards for 4 meters. Vertically downward for 4 meters, takes a turn, moves for another 4 meters. So 4 plus 4 plus 8 plus 4 plus 4 again plus this 10 meters plus 6 plus 6. See, 4 plus 4, 8, 4 plus 4 plus 12 meters here, because you have to move from intermediate pile to this point. Intermediate pile to the downstream pile. So you have 6 meters, 4 meters, and this is 10 minus 8, 2 meters. So total 12 meters plus 6 vertically downwards plus another 6 vertically upwards. So your total length of creep is 48 meters. So the hydraulic gradient will be H by L. H by L. So the total head of water is 4 divided by 48, 1 by 12. Okay, 1 by 12. Hydraulic gradient is 1 by 12. Now, uplift pressure at point A. So this point A is at a distance of 5 meters. This point A is at a distance of 5 meters. So what is the total creep length up to the point A? The total length of creep up to point A will be 4 meters vertically downwards plus 4 meters vertically upwards plus 5 meters. 4 plus 4 plus 5, 13 meters. Correspondingly, what is the residual seepage head which is available at point A? At point A, H1 will be equal to 4 is the total head. The residual head will be 4 into 1 minus creep length is 13 for against a total creep length of 48 meters. At the point where the creep length is 13, against a total creep length of 48. So 1 minus 13 by 48 would be the residual seepage head, 2.92 meters. So uplift pressure will be gamma H1. Gamma H1 is the uplift pressure. So gamma 9.81 kilonewton per meter cube into H1 is the residual seepage head at this point. which is equal to 28.61 kilonewton per meter square. Correspondingly, the thickness required will be 4 by 3 into h1 by s minus 1. So 4 by 3 into h1 is 2.92 divided by s is 2.24 minus 1. So you got the thickness of the floor required at point A is 3.14 meters. The floor thickness required at point A is 3.14 meters. Similarly, at point B, so what is the residual head? So you need to find the total creep length up to point B. Up to point B, the total creep length will be 4 meters vertically downwards plus 4 meters vertically upwards plus 8 meters horizontal. 8 meters horizontal. Then 4 meters downward plus 4 meters vertical plus another 2 meters here. Another 2 meters to reach point B. So total 26 meters. Correspondingly, the residual seepage will be 1 minus 26 by 48 into the height of water, head of water 4 meters, 1.83. Correspondingly, uplift pressure gamma H2 and the thickness of the floor will be 4 by 3 into h by s minus 1, 1.97 meters. Similarly, at point C also, same procedure, 1.43 meters. You may note here, as the distance from the weir is increasing alongside the downstream portion, we have reduction in the thickness because the seepage is getting reduced, the thickness of the, uplift pressure is getting reduced. Accordingly, the floor thickness also is reduced. See, 3 meters has come down to 2 meters, it has come down to about 1.5 meters. About 1.5 meters. So this is a problem where we try to calculate the residual height. Correspondingly, what is the thickness of the floor required to be provided. So we discussed basically in this class about 3 theories: Bligh's theory, and what are the assumptions made by the Bligh's theory, what are the limitations of this Bligh's theory, followed by what is the modification made by Ellie on Bligh's theory based on the limitations of the Bligh's theory. Then Lane's weighted creep theory also we discussed, and we had taken up one problem on the Bligh's creep theory. So this closes about the topic on Bligh's theory, and next class we go for other topic on cost loss theory. Thank you very much. Thank you.